Okay. Hello. As announced, my name is Arne Brutschy. I'm the CTO of Rise Financial Technologies. We are a London-based technology provider, and we're bringing DLT infrastructure to the post-trade industry. So DLT means blockchain. I guess most of you have heard already about blockchain. There's kind of a hype around. So we have a first product that focuses on issuance, settlement, and record keeping. So issuance of assets into DLT environments, and then settlement, so transfer of ownerships within these environments. We have past and current projects with Swift, CSDs, banks, focus, for example, on commercial papers, ABS, and other types. So our product at the moment is a custom-made, targeted use case focused DLT system for settlement in the post-trade industry. And in this presentation later, I'll explain why we decided to go for this particular custom-made product, and because it has very much to do with testing and QA. Just to start off, I'm going to present what happens if you don't get it right in a DLT system. So Bitcoin, everybody knows Bitcoin in 2010, they had, for example, two critical bugs. One, for example, allowed to create unlimited money, which actually happened. By today's standards, that would be something like $230 quadrillion. Luckily, the project at this time was so early that they were able to roll it back. Shadowcash is something rather obscure, but I included it because it had a different kind of problem. In blockchains, all data is shared among all participants, and they are they offer a anonymity-focused currency, and they actually had a very subtle bug in their cryptography libraries, and that allowed attackers to lift all anonymity for all users of the system. And everybody, I guess, heard about the Ethereum DAO bug, a virtual investment fund that had a critical bug in their smart contract, and they lost $53 million because of that. What that means, all financial systems, they are critical, they're handling money, so you better get it right. But in blockchains, there are a couple of attributes that make it much more complex. Mostly, everything is public if you have a public blockchain. If it's out there, it can be attacked. You cannot roll it back. You cannot fix it, or not easily. And also, because of shared data, there might be that confidentiality among participants is easily affected. So getting it right in blockchains is pretty important. So how do we do that? We use software testing and QA. As we are a software development shop, I'm going to focus in this presentation on rather technical part of software testing. And I'm going to focus on the challenges that we are facing rather than established testing strategies, simply because this industry is at its infancy, this technology is, and there are no standards, no industry standards for the software itself or the processes in it, and accordingly there's no special established testing strategies. So we can apply known strategies to the problems that we're facing. So I'm going to focus on two main areas, is the DLT system itself, and then the validation rules and smart contracts. These are not the only, this is not exhaustive, but these are the two main points where basically DLT systems differ from traditional transactional systems. So just an intro. Who heard about blockchains? Who knows what it is? Okay, very good. Does anyone work with blockchains? Oh, yes. So I have this very nice quote from Richard Brown from R3, which reads, "Distributed ledgers are systems that enable parties who don't fully trust each other to form and maintain consensus about the existence, status, and evolution of a set of shared facts." Now, that is quite a mouthful, but basically it means we have a shared distributed database. And the key differences are we have shared control and we have limited trust. Because sharing data was easy. We did this since decades. And even having shared data that can be changed by multiple parties existed also in the form of consensus-driven databases. But what we have now is we have shared control and we have limited trust, so we can employ this in environments where you have trust boundaries. You need to cross trust boundaries. That also means that basically blockchains are only, or their main usefulness are in those environments. So just to explain what I mean with shared control, in a traditional system, you typically have a database operator. This operator has the control by power. You can see this here on the left. The blue person there is the database operator, is the trusted operator, and the consumer at the bottom, they issue instructions, they access the data, and so on and so on. There's some sort of agreement how they work together. Probably there's some contracts, but in the end, control lies with the operator, and the others have to trust the operator. In a DLT world, the operator gets disintermediated. So that means the consumers are also fully in control of the data. They all have their own copy of the data, and they follow a certain set of rules by which they modify the data. So whenever there's a transaction coming into the system, they agree on whether this is valid or not, following these rules. So coming to the actual DLT system, what are the challenges that we are facing when implementing something like this? So distributed ledger systems are distributed systems. No big surprise here, but basically that means they are a great deal harder than conventional TX processing systems. So it is notoriously difficult to control them because they are non-deterministic. They are probably, well, they're distributed. They might be even globally distributed. They might be very large. And as such, testing in them is pretty hard. So they are comparable to a massively interconnected banking system. You have delays, you have frequent lags, connection losses, network splits, all these kind of things. But you're sharing potentially diverging data, and everything is executed in concurrency, independent failure modes, and so on. It's not easy, let's say. So test strategies for systems like that is, it's the same as for other distributed systems. So you try to isolate as far as possible. You try to make it deterministic, and then you inject faults, and you see how the system behaves. So first you start testing each component in isolation. It's quite useful to even have componentization on the level of an individual node. So this is a node, that means it's a participant in the network. The full network, the whole blockchain system, so every of these earlier participants runs one of these, and you have a whole network of them running the same copy of the same software. Then you start testing the system in a tightly controlled environment. So here you have the whole network ideally on the same machine, so that you can still tightly control, make it deterministic. Maybe you need to simulate the network and try to get to a point where execution is deterministic and you can see how the system behaves, and most important, get deterministic execution. And then finally, you need to deal with non-determinism. So you need to set up the system such that it runs over normal network links. It might diverge across different runs. And then here the strategy is that you record how the system behaves. You're able to replay it, and this allows you to do regression testing and basically fixing. And at this point, it's quite important that also you start to inject random faults into the system. So I guess maybe some of you have heard of the Chaos Monkey. It is a famous program employed by Netflix. which is just a program that goes into Netflix's infrastructure and randomly shoots down servers and components. And a similar strategy is followed by us, where in our test environments, in the long standing test environments, we randomly inject faults and shoot down components, and thereby injecting random faults. Further challenges with DLT systems is you're facing adversarial environment. So you're crossing trust boundaries. So you have to assume that the whole system can be attacked. You cannot rely on ring fencing, firewalling, these kind of things. You need to think about the system as a whole, and you need to protect it in the end by the system design and cryptography. Non-functional testing is pretty hard in these kind of systems to ensure, for example, and do stress testing, load behavior, and so on. Security testing, a DLT is essentially a cryptographic system. Some of these cryptography methods are rather new, so it might be that some of your assumptions don't hold simply because the underlying math isn't correct, and this is something that might be discovered years down the line. So it's not really something you can test for, but it's a threat. And then in the end, version and change management is pretty difficult because the system, once it runs, you might lose control over who runs how much software or what version of your software. So this is actually one of the problems with Bitcoin, that they have a political issue and they can't force everybody to upgrade the software, and therefore it's pretty hard to evolve the system and improve it. Okay, so coming to the second part or the second area I wanted to talk about is the validation rules. The validation rules are basically the rules by which the network participants agree on what is valid and what is not. So which modification to the shared database is allowed. And they follow a set of shared rules, the validation rules. And we can hard code them, or we can have them in a more flexible manner, and they might even be ad hoc supplied by every user, which is called smart contracts. And as these are the rules that, basically the business rules by which we can transform and modify data, it's quite important that we get these right. And there's a clear trade-off between complexity, flexibility, and security. So the challenges here is that first we need to make them behave absolutely the same across a quite diverse system and architectures. And then the more complex the rules, the larger the state space. So that means the more flexibility we have in our rules, the harder it is to tightly control it. So generally we try to keep it simple, try to keep it self-contained, and we try to keep it stateless. But again, this opposes flexibility. So, it ate up my slide, but basically that's supposed to be a spectrum from hard-coded to ad hoc validation rules, where on the one hand side you have very little flexibility, but you can tightly control your state space, you can test it very thoroughly, while on the other side of the spectrum you have a lot of flexibility, but it's really hard to test and do QA on it. And the other side of the spectrum, the one here, which is super flexible, is called smart contracts. So it's a bit all the rage in the industry right now, so I'm going to go into a little bit of detail at this point. A smart contract basically is a program that you can deploy onto the blockchain. So there's a two-step process. There's supposed to be a two here. So in the first step, a user deploys a program onto the blockchain. The blockchain sort of acts like a shared computer. So when the user invokes the program by sending parameters into the program, it gets executed, and all the nodes agree on the result of the execution. So you can be sure that your program is executed according to the rules written in it. And then you get the result, and any sort of state is saved in the blockchain itself. This has quite some important implications, because basically they transfer the risk from the DLT provider to the DLT user. So in a hard-coded system, you provide a product, and you're sure that your product follows a certain set of business rules. And it's the DLT provider's responsibility to ensure the quality of these rules and the implementation of them. If you have smart contracts, it's the user that submits these contracts and therefore can define these rules. So they have to do testing and QA. Now the problem is that most of these programs, these smart contracts, are expressed in languages that are Turing complete. They have a high complexity, infinite state space. And additionally, these programs, once deployed on the blockchain, might interact with each other. So your program might depend on data or execution from a smart contract provided by someone else. So that means from the user perspective, you depend on a program that potentially interacts with other programs that are not under your control in a distributed non-deterministic system in a dynamically changing and expanding network using evolving rules and features, because the DLT system will also be changed and maintained and evolved over time. So as you can see, smart contracts are impressive technology because they're extremely flexible and that allow you to map different use cases, a large variety of business processes onto a DLT platform. But on the other hand, they're really hard to control and to get right. So in summary, basically the main testing challenges in DLT systems is that it's a distributed system, even worse in an adversarial scenario. That the testing of validation rules is crucial, and that smart contracts is, let's say, due to the transfer of risk and the loss of control of it, even more an open problem. So our recommendations basically at this stage is to try to limit the scope, choose a use case that benefits from DLT and develop a custom-made software for it that allows you to tightly control the quality of the software and the quality of the validation rules and test this accordingly. And this is exactly what we have done for the post-trade industry. And if you have any questions and want to talk about it, please contact me. Apart from that, any questions?
Thanks. So I'm confused about the role of fault injection here. I mean, the whole point of blockchain and contracts is that you have integrity, using a shared ledger. So what faults are we talking about here?
Well, you gotta build the system that is has integrity. So it's mostly faults at the level of consensus algorithms. So when you build your system, you have an algorithm that achieves consensus according to the rules, to the validation rules. And this one is, of course, dependent on the properties of the system, and you need to make sure that it works properly. So that is basically what you're testing, the DLT system itself.
So prior to blockchain, the preceding sort of layer of the system is what you're talking about?
Sorry?
Prior to blockchain, the preceding layer of the system is what you're describing?
Sorry, I didn't understand.
Prior to blockchain is what you're describing here. Right?
Prior to blockchain?
Before it touches the storage layer.
Basically, the core of the blockchain system is this algorithm, how participants agree on the validity of transactions, right? So basically checking these rules and finding agreements among the nodes in the network. And that's a pretty difficult algorithm to get right. And so these algorithms are tested through fault injection because they are, for example, you have different trade-offs, but they are liable to you get problems with transmission delays, network splits, and so on.
Hi, how do you make tests repeatable in this environment? I suppose if the whole idea of the network being unreliable and whatever, at what point are you confident that issue has been resolved, I suppose?
Yes, it's pretty hard to make this to do regression testing in these sort of non-deterministic environments. So we try to filter as much as possible in the tightly controlled test environment where we get rid of non-determinism, for example, by abstracting the network or putting everything on one machine. But at some point, you need to have a more realistic testing environment, and you can only solve it by recording fault states, replaying it, and then check whether the problem has been resolved in the replayed data. So that's the only option.
Any more questions? All right. Thank you very much, Arne, Brutschy.